Well, number 19, they want to know what the fundamental frequency is for a bottle that has a length of 0.22 meters, that is 22 centimeters. So now, since this is a bottle that's open at the top and closed at the bottom, we know that at the top we have to have an antinode, and at the bottom we have to have a node. And so that's going to mean that at the bottom, the pressure can't fluctuate really at all, versus at the top, it can fluctuate a lot. And so when we draw that as a transverse wave, even though we know the sound is a longitudinal wave, we're going to draw this picture right here with the antinode here at the top and the node down here at the bottom. Okay, so what I just drew right there for you was a fourth of a wavelength. And so we're going to say that this length of the bottle, 0.22 meters, that length is a fourth of a wavelength. We're going to say then that the wave speed is the fundamental frequency times that fundamental wavelength. And that fourth of the wavelength I was talking about before was the fundamental. And so now they want that fundamental frequency, so I'll take that wave speed and divide by that fundamental wavelength, or the wave speed divided by 4 times the length of the bottle. So now I'll just wrap it up with 343 meters per second divided by 4 times 0.22 meters, that is 0.88 meters, and you're going to end up with 389.77. Using significant figures, we'll round that to 390 hertz. If that were the case, that bottle was empty like that, you would hear a sound something like this. On number 20, they say, what's a third harmonic frequency for a bottle that has a height of 0.18 meters? Now, you could go straight at this and get an answer very quickly. You could think, all right, the third harmonic frequency is going to have 3/4 of a wavelength in the bottle. So if I wanted to draw a nice job, do a nice job here, I'd try to split this up into thirds. There we go. And I have to have that node at the bottom, and I have to have that antinode at the top. And now, if I want 3/4 of a wavelength, I'm going to draw a crest. Remember, this is supposed to be a longitudinal wave, but that's just our way of showing the pressure, and a part of a trough, half a trough. And so then I'll draw the mirror image of that over here, and that's an okay looking picture, maybe not my best work. Now, I know that length is showing me 3/4 of that wavelength, and that's wavelength 3. It goes along with the third harmonic frequency. So that means that that wavelength 3 is 4/3 of the length of the bottle. And so 4/3 of 0.18 meters, you can do that in your head, 0.24 meters. Okay, so now if I want frequency 3, just like I did on the last example, I know that that's the wave speed divided by that wavelength. And so I'll make it wave speed divided by 0.24 meters. I should have put a 343 meters per second in there, and I end up getting 1429.17. Significant figure wise, let's make that 1400 hertz. Okay, so that's one way to just go straight at the answer. 1400 hertz is the answer. Now let's learn a little bit more from this though. So say I did blow across that bottle, and I'd actually get a sound that had some harmonic content in it. And if I put it into a microphone and split it up into its individual frequencies, you'd see something neat. Here's what you'd have. So in that sound, you'd have the fundamental frequency. Now, we drew this on the last one. The fundamental frequency has that antinode at the bottom, node at the bottom and antinode at the top. And it's going to be something like this. And so frequency 1 is going to give you that. Now, if you doubled that frequency 1, you'd get frequency 2. Now, if you know a little more about this, you know that what I'm about to draw has an issue, and we'll have to talk more about this. But frequency 2 would have a wavelength that was only half as long, and it would look like that. So, and now again, you should say to yourself, wait a minute, I don't know about that picture. We'll talk more about that in a second. Frequency 3 is what I just drew a second ago. This is nice. I get another shot at this. Now that actually looks a lot better. Frequency 3 would look like that. Okay, so now we know that the length of this bottle is 0.18 meters. And so say I didn't do that for that last part. Say I said, all right, well, then this is that 0.818 meters is the length, and it's also a fourth of that fundamental wavelength. So I might say that that fundamental wavelength is 4 times the 0.18 or 0.72 meters. Now, I could say frequency 1 is the wave speed divided by wavelength 1, 343 meters a second by 0.72 meters, and I would get 476.39 hertz. Only 2 of those digits are significant, but I'm not going to round it off because I'm going to do something with that number. Okay, now I could take that number and I could multiply it by 2 to get the second harmonic frequency. So frequency 2 is 2 times frequency 1, so 2 times that 476 would give you 952.78, and this one I'm not going to say any more about, so 950 hertz. And if I took this 476 fundamental frequency and I multiplied it by 3, I'd get that third harmonic. Now, you're going to get that same 1400 hertz that I got a second ago, but I just got it in a little bit different way. All right, so say you blew across the top of the bottle and you heard this sound, and it wouldn't just be a single tone. It would have in it that 476. It would have in it that 1400 hertz. And it would not have in it the 950. And so if you played this into a microphone and you did an analysis on this where it was broken down into its individual frequencies, you would get here a lot of frequency 1. Right there where frequency 2 is, you'd expect to get something, but you'd actually have a lot of nothing. And frequency 3 would be there. It wouldn't be quite as strong as frequency 1, but it would still be there. Now, why is frequency 2 absent whenever you play this bottle? Well, it's because on a bottle that's closed on the bottom, you have to have a node, and if it's open at the top, you have to have an antinode. And you can see that that's not what this frequency gives. So this will not give you resonance. So this is not going to be something that is going to be represented in the actual sound. So we say that we have our fundamental frequency, we have our third harmonic, and we do not have our second harmonic. A music type would say that we have this as our fundamental, and then an overtone, which is a frequency that's higher than a fundamental that is also present, is going to be this frequency 3. And so they would call this the first overtone. Number 21 talks about the fundamental wavelength of a particular bottle, and it is 0.88 meters. And they say, what's the length of the bottle? Well, when we're talking about the fundamental wavelength, we're talking about whenever you have a node at the bottom and you have an antinode at the top, and it's going to look something like this. And so what I just drew there was a fourth of a wave. The fundamental wavelength is 4 times the length of the bottle. And so the length of the bottle is 1/4 of the fundamental wavelength. So that's 1/4 of 0.88 meters, and that's 0.22 meters. On example 14.5, you're going to use this bottle as a musical instrument, and you want to put enough water in this so that when you blow across the top, it makes a sound that has a frequency of 525 hertz. So the bottle's 26 centimeters tall, and most of us don't have the ability to make a bottle any size we want, at least the glass part, but we can fill the bottom of it with water, and that's just as good. And so it's 26 centimeters tall. Well, let's ignore that for now. Let's figure out how long of a bottle do we actually need, and hopefully it's shorter than 26. We'll fill up the bottom with some water, and the air that's left will be the amount of distance that we need to get that frequency. Okay, so I know then that frequency 1 is going to be 525 hertz, and I know that the wave speed is the frequency times the wavelength as long as they have the same number. So that means that the fundamental wavelength here is going to be the wave speed divided by that fundamental frequency. If you go with 343 meters a second and divide it by the 525 hertz, you're going to get a fundamental wavelength of 0.653 meters. Now, you know that the fundamental wavelength is going to stick way out of the bottle, right? They're going to have an antinode or a node down here at the bottom. You're going to have an antinode at the top, and so it's going to be a picture something like this. Well, I've only shown you a fourth of it. It keeps on going way off the page. So we're going to say that the length of the bottle that we want is going to be 1/4 of that fundamental wavelength. And so 1/4 of the 0.653 meters that I had from before is going to be 0.163 meters, or 16.3 centimeters. I want the air to be 16.3 centimeters long. The bottle itself is 26 centimeters. So I'm going to say that I'm going to do 26 centimeters minus 16.3 centimeters, and that's going to give me 9.7 centimeters of water, so that I get 16.3 centimeters of air. Now, on the follow-up for number 22, it says, what's the frequency of the next higher harmonic above the fundamental? I wish they had said that you'll actually hear in the sound, or that will actually appear in the sound. We know that we get harmonics by just multiplying the fundamental frequency by integers. But on an open-closed tube like this, even multiples don't give you any resonance and will not appear in the sound. And so I can say that I have frequency 2, that's 2 times the fundamental frequency, but this will give you nothing, because that would set up that node at the top and bottom. Look at the last couple examples for that, if you need a little brushing up on that. Frequency 3 will work, though, and that will be 3 times that fundamental frequency. Why is frequency 3 going to work? Well, just in short, if I have a picture that looks kind of like this, I have that node at the bottom and I have that antinode at the top, and that will give me the resonance. And you will, if you play the bottle, you'll actually see that this frequency will be in the sound too. 3 times that fundamental, 525 hertz, will be 1575 hertz. And number 23 is about a pipe that's closed at one end and open at the other end. They don't say that, but I'm assuming that. And it has a fundamental frequency of 330 hertz. They want to know how long the pipe is. This is a lot like the last example that I did. We know that for the fundamental frequency, it's 1/4 of that will fit inside of the pipe like this. And so we know that the wave speed is the wavelength times the frequency, as long as those numbers match. And so I'll say that that fundamental wavelength is the wave speed divided by the fundamental frequency. How about 343 meters per second divided by the 330 hertz? And I get 1.039 meters. Now, this is much longer than the actual answer, because this is the wavelength, and I want the length of the pipe. And we know that the length of the pipe is 1/4 of that fundamental wavelength. So 1/4 of the 1.039 is going to be 0.2598 meters. How about 26 centimeters? Number 24, it says the wavelength of the third harmonic in a bottle is 0.22 meters. What's the length of the bottle? Well, if they talk about the third harmonic in a bottle, we've drawn this a couple times already on this video. There's the open end, which has the antinode, and the closed end, which has the node. Maybe a good idea to split this into about thirds so the picture looks pretty good. And now I have this node here, antinode over there, showing the mirror images of it there. Okay, so now you can see that the length of this bottle, L, there we go, is equal to 3/4 of this third wavelength. So how about 3/4 of 0.22 meters? And that's going to be 16.5 centimeters, 0.165 meters. You're going to round that to 17 centimeters. A good conceptual one here on number 28. It says, what are the conditions necessary for a standing wave in a pipe that's open at one end and presumably closed at the other end? Well, first thing, you have to have something that's vibrating on one end. But just not vibrating at any old frequency. It has to be vibrating at a frequency so that when you multiply that frequency by 4 times the length of the tube, you get the wave speed, 343. And so here's what I mean. You can have a tube, let's say it's this long. And if I want to draw the fundamental for you, I'd draw that node over here. I'd draw that antinode over on this open side. And I would draw this picture like this that you've seen a few times in this video. Now, there has to be something vibrating out here. Maybe an easy thing to draw is a tuning fork, and the tines are vibrating back and forth. Now, any old tuning fork won't work. It has to be something that whenever you take that frequency right there, we're going to call it frequency 1, we'll say this tuning fork does work, times that fundamental wavelength, which I haven't drawn here. It's 4 times as long as what I've drawn here. You get that 343 meter per second speed of sound in air. So I have to have a frequency so that I take that wave speed and I divide by that fundamental wavelength, and that quotient gives me that frequency, or I take that wave speed, divide by 4 times the length of the tube, and I will get that frequency. If I have those two things, so I have something vibrating, and not just something vibrating, but something vibrating at a frequency that's equal to this quotient, then I will get that standing wave in a tube. But I could also have a frequency that was 3 times higher than that. And so I could have the same tube, but I could have it split into thirds, something like this, third, third, and now I'll draw this for you. There you go. And so now this frequency would be 3 times higher, because now you can see that this wavelength is only 1/3 of what it used to be. And so I could have this tuning fork out here, and its frequency could be something so that I have the wave speed divided by that third wavelength, or the wave speed divided by 4/3 the length of the tube. So you can see that 3 times the fundamental frequency will work, 5 times the fundamental frequency will work, 7, 9, 11, any odd multiple of that fundamental frequency will work. On number 81, they're showing you an organ pipe, and it's 2.75 meters long. It says it's closed at one end, open at the other end. What's the frequency of the standing wave shown in this pipe? Now, by now, we can recognize this picture as what you're going to get with the third harmonic, what you're going to get with the third wavelength, and we know if we multiply those two things together, we're going to get the wave speed. And so I could say that the wave speed here is the frequency times the wavelength. They want the frequency, so we could say the frequency is the wave speed divided by the wavelength. Now, you can see here in this length of the tube, I see half of a wave, another fourth of the wave, 3/4 of that wavelength, and we know that that's wavelength 3. So I could say that that wavelength 3, since the length is 3/4 of wavelength 3, wavelength 3 is 4/3 of the length of the tube. And that just says that the third wavelength is longer than the tube is. And so 4/3 of the length of the tube, that's going to be 343 meters per second divided by 4/3 of 2.75 meters. And if you run that in the old machine, you're going to get a frequency of 93.55 hertz, 3 sig figs on that. And then on part B, they say, what's the fundamental frequency of the pipe? And that's really easy. We know that frequency 3 is 3 times frequency 1, so frequency 1 is a third of frequency 3, and so it's a third of the 93.55, and it's going to be 31.18 or 31.2 hertz.